Good morning, guys. Just a second here. We can get started. I hope everybody had a safe and enjoyable holiday. I was taking a look at completion rates in WebAssign yesterday around 2 p.m. So I'm not sure where everybody stands now, but as of that time, it seemed like a lot of folks were still wrapping things up. But kind of regardless, we have to move on. So that is what we're going to be doing. Everybody switched over here. Okay. So this, of course, is Calc 2. Today is the 9th. And as promised, today we're going to start on Chapter 7. We're going to start learning new methods of integration. So we are done with the volume problems of last week. And this is kind of the start of the main bit of the course. So you can kind of think of the last couple of weeks as warm-up. But then today we really begin the meat of Calc 2. So you're going to learn how to integrate all sorts of things. And the first thing you're going to learn is the backwards product rule, which is called integration by parts. So today we're going to start section 7.1. Integration by parts. Okay. Yeah, that's good enough. So like I said, this is a total change of perspective. We're not going to be looking at geometric arguments very much here. We're not going to be sketching lots of regions or imagining rotating anything about anything else. We're just going to be given an integral and asked to solve it. And we'll be doing something like that all the way until we're ready for exam 1. For those who are kind of playing the home game, everybody's playing the home game now, right? Keeping track and seeing what is coming up when. We are not too far away from our first test, so you want to keep an eye on the syllabus. So we are here, which means exam 1 about 2 weeks away. So what is integration by parts? There's a bunch of integrals we don't know how to do yet. I know how to integrate e to the x. But what do you do if I slap on an x? How do you integrate x e to the x? Or in general, any polynomial times e to the x? Or even, God forbid, the natural log of x. We don't know how to integrate that. The list goes on. Lots and lots of things we don't know how to manage. All of these things that I've listed here will fall to the methods of section 7.1. And in particular, these two guys are kind of classic examples. So the theorem, I'll just state it. I'll refer to it as IBP, stands for integration by parts. So I don't have to write integration by parts every single time. It can be written in two ways. First, there's the way you write it for an indefinite integral. So it can be written as this. So here u and v are functions. Usually of the variable x. The other way you can write this is for definite integrals. It doesn't change a whole lot. The thing is, people forget this middle part. So this is the theorem. And the same thing here, where u is a function of x and v is a function of x. So usually the way we'll make use of this theorem is someone will hand you an integral like this. Part of it may be like this piece I'll call u, and the rest of it you'll call dv. Then you apply this formula, usually by writing on a table that has all four things, u, v, du, and dv. That's all right, Amanda. I'm still coming up to speed myself. This 8 a.m. shit is hard. So I think the best way to get a feel for this is really just practice. Let's start attacking some of these problems we haven't been able to do previously. So the first one that I'd like to do is x times e to the x. This is an integral that we certainly should be able to do. E to the x is one of our fundamental transcendental functions, and multiplying by x shouldn't make things too much harder. But basically, you should think of this as a backwards product rule, right? This thing I would differentiate with the product rule if I was going to differentiate it. So integrating it, my first thought is integration by parts. So for example, I would like to do the integral of x times e to the x dx. The way I'm going to do this is by making an IBP table. Here's how that goes. You pick u and dv. I'm going to pick u to be x and dv to be e to the x dx. The way this is going to shake out, I'll give you a rule for how to choose u, and then you'll let dv be everything else. But it's up to you how to choose these, as long as u times dv is the whole integrand. That's the main thing. So you have to pick u and dv as a partition of your integrand. So you split your integrand up into two pieces. One of the pieces you call u, the other piece you call dv. Then you calculate du. So here if u is x, du is just dx. And you calculate v. If dv is e to the x dx, then I would integrate on both sides to get v. The integral of e to the x dx is just e to the x. So here is my IBP table. And then you apply the formula. The integral of u dv is what I have right here, because u is x and dv is e to the x dx. And according to the theorem, the integral of u dv is u times v minus the integral of v du. So you look at your table, you take u times v minus the integral of v times du. So according to the integration by parts formula, this integral is equal to u times v, which is x times e to the x, minus the integral of v times du, which is e to the x dx. And this first piece here is done. If it was a definite integral, I would have to evaluate between some bounds, but since it's an indefinite integral, this first piece is done. But I still have to integrate the e to the x. This is x e to the x minus, what is the integral of e to the x? Oh yeah, that's e to the x. And then I slap on a plus c at this stage because there's no more integrals. So here's your answer. So again, the way this works, you take your integral and you split it into two pieces. One of those pieces you call u, everything else you call dv. Then you just make this table. So you take u, you differentiate to get du, you take dv, you integrate to get v, and then follow the formula. So these formulae, these are the things that you need to remember for section 7.1. I'll do one or two more examples, and then I'm going to give you that rule that helps you choose u and dv. Any questions on the example we did at the bottom of the page here? Questions on how we got that boxed answer or what we did in between, why we did it that way? Okay. Another family of functions that this is useful on. Let's do the integral from 0 to pi. How about, yeah, 0 to pi. T times sine of t dt. So same sort of thing. I've got like a polynomial times, that's not e to the x, but it's a transcendental function. So polynomial times a transcendental function. Again, I'll run IBP. And again, I'll pick u to be the polynomial piece, and I'll pick dv to be everything else. So that's sine t dt. T. Then I'll differentiate u to get du. Du is just dt. I'll integrate dv to get v. So if I integrate sine of t, who differentiates to sine of t? That's negative cos of t. So here's my little IBP table. And then I just follow the formula. It says that the integral of u times dv should be equal to u times v. So that's t times negative cos t, or negative t cos t, evaluated between bounds. Don't forget this part. A lot of people forget this, the evaluation. Minus the integral from 0 to pi of v times du. Now my recommendation is to go ahead and do the evaluation step before you do anything else. Go ahead and get this cleared up, because sometimes the integral that lingers over here will take a while, and you don't want to copy all this shit down when it could simplify to something very simple. So if I plug in pi of negative pi times the cos of pi, the cos of pi is -1. So that's negative pi times -1, that's just pi. And then I'll subtract what I get when I plug in 0. When I plug in 0, I'll have -0 times the cos of 0. That's -0 times 1, which is just 0. So this whole piece here evaluates just to pi. And then here I've got minus the integral of negative cos t. That will just become plus the integral from 0 to pi of cos t dt. And then finally, I want to go ahead and, and do this guy. So what's an antiderivative for cosine? Oh, sine. So this will be pi plus sine t evaluated from 0 to pi. And this is the sine of pi minus the sine of 0 both of which are 0. All right, the sine of pi is 0, and the sine of 0 is 0, so this whole apparatus is just pi. So these are two very basic integration by parts examples where you have a polynomial piece times sine, cosine, or e to the x. Those will always go the same way. You'll always pick u to be the polynomial piece, and then dv to be everything else. In both of the examples we've done, the polynomial has been a degree 1 polynomial. It's just been like x or t. But if this is a higher degree polynomial, then what you would find is that your du would be 1 degree less. And you would end up here with something, if this was like a t squared, this would be like a t cos t. If this was a t cubed, this would be like a t squared cos t. And so you'd have to repeatedly run integration by parts until you knock the power of that polynomial down to a place where you can integrate just the transcendental function. But we're still warming up. We're still just getting used to this stuff. I want to show you a different kind of example here. So I mentioned that one of the functions we don't know how to integrate yet is the natural log. All right, this is not a problem we've been able to solve yet. We haven't even attempted it. And the trick here is integration by parts. But I can't follow that same sort of reasoning that I was before. I'm going to pick u to be the polynomial and dv to be everything else because there is no polynomial piece here. There we go. Instead, what I'll do, so I have to split my integral up into u and dv pieces. Here I'll pick u to be the ln of x and dv to be dx. So here is the integral of u times dv. Right? If I pick u to be ln of x and dv to just be dx. And now I'll fill out my table. Du, the derivative of ln x is 1 over x. So du is 1 over x dx. And if we integrate dv equals dx, we just get v equals x. I imagine now you're starting to see why I said, I don't like using the letter u for a substitution, because if this said ln of u, then this could get very confusing. If I go ahead and run my IBP formula now with this table, u times v is x times the ln of x. And then minus the integral of v times du, that's x times 1 over x dx. But this integral isn't hard. X times 1 over x, that's just 1. The x's cancel. So this is x ln x minus the integral of 1 dx, or just dx. And the integral of dx is x. So this is x ln x minus x plus a constant. And so there it is, the integral of the natural log for the first time. We've never been able to do that before. So IBP is going to open up a whole universe of integrals that we previously couldn't do. In fact, IBP might be the most important technique I teach in chapter 7. We're going to learn a bunch of other techniques, but IBP, probably the one that will be applied to the greatest number of things, both within this course and beyond this course. It's a legit research technique. If you're trying to figure something out in a genuinely hard problem, just seeing what happens with a few different approaches of integration by parts is a totally valid thing to do. So we'll take a second for questions on these two examples. Why did they shake out the way we did? Why did each line look the way it does? Make sure you have these clear in your notes and you understand what happened there. And then I'll show you that rule for picking u and dv.
Questions on this first guy? C is an arbitrary constant, so plus C or minus C really doesn't matter. You can write it as plus C or as minus C. If C is allowed to run over all real numbers, then minus C also runs over all real numbers. So it really doesn't matter whether you write this as a plus C or a minus C. Fair question, though. Remember, the idea with the indefinite integral here is that this is kind of like your fundamental antiderivative, and you could slap any constant on at the end here, and you'd still get something that differentiates to the natural log of x. So I don't care whether this is a plus or a minus. Any other questions on this? So we're all comfortable with like this line, how this line follows from this box and the IBP formula from the previous page? Yeah. We include the C only for indefinite integrals. So if it was a definite integral, like up here, with bounds, there's no plus C anywhere, right? But for an indefinite integral, there is a plus C. So only indefinite integrals get the plus C. An indefinite integral is an infinite family of functions, right? An object like this should be every function in the world that differentiates to natural log x. There's infinitely many of them. And the way we describe them is like this. It's all the vertical translates of this function. So it's this function plus an arbitrary constant. A definite integral is always just one particular number. It's the area bounded by this function from 0 to pi. So there's never a plus C for definite integrals, and there's always a plus C for indefinite integrals. So we have to remember what the integration by parts formula says. It says the integral of u times dv is equal to u times v minus the integral of v times du. So sine t dt is what I chose to be dv. And nowhere on the right-hand side of my formula does dv show up. That's kind of one of the nice things about integration by parts. So here I have u times v evaluated from 0 to pi minus the integral of v times du evaluated from 0 to pi. So it's kind of just the way the formula shakes out, that the sine t piece here, the dv piece here, doesn't show up anywhere in the next line. And we're just kind of following the formula. I'll give you a little proof of the formula. There's actually a proof of the formula up in the modules page.
Excuse me, sir.
Mm-hmm.
For the first example, where you say integral t sine t dt, so you consider t like u and sine t like a v. But on second example, you consider dx like a v, like dv. So I don't understand. So if we don't have two functions, we have just one function plus ds or dt or du, so we have to consider like a dv.
That's the idea. You have to take whatever you're given and split it into two pieces. One piece you will call u, and the other piece you will call dv. I could have chosen u to be t times sine t, and dv to just be dt. That would be another valid way to start this problem. But if I started it that way, it wouldn't come out nicely. So the idea here, let's get to the place where we can start discussing the decisions. So here's the procedure for integration by parts. Okay, you're given an integral. And you don't see any other way to do it. You don't see a substitution or an obvious antiderivative. In other words, you're given an integral that you don't know how to do. It's not one of the things we've seen before. Then you partition the integrand into two pieces. One you call u, and the rest we call dv. Then you complete the IVP table. Calculating du from u and v from dv. Then you plug the elements from the table into the IVP formula. And then really the challenging part is here in step 1, where you have to choose your partition. Does everybody know what a partition is? So when I partition a set or I partition an object, that has a very particular meaning. It means you're going to take all the shit and split it into multiple pieces that don't overlap, and that when you join them together, you get the whole thing, right? So a partition of all the pens in this cup would be me taking some of the pens here and some of the pens here. There's no overlap. There's no pen which is in both hands. And if I put them all back together, that's all the pens. That's a partition. You partition your integrand into two pieces, and it's totally up to you how you do that. One of the pieces you call u, the other piece you call dv. And it's up to you to choose how you split that, right? I could take one pen and call this u, and take all the other shit and call this dv. Or I could split them 50-50, or I could split them any other number of ways. So it's up to you to choose the partition. I'm going to give you a rule that'll help you choose the partition in most cases wisely. But this is where the creativity is. Once you have a partition, once you've chosen part of your thing to call u and the rest of it to call dv, then you fill out the table. So you've already got u and dv, you chose those. So that means you calculate du, you get that by differentiating u, and you calculate v, you get that by integrating dv. And then you'll have all four of the pieces that exist in that formula, so you'll plug them into the formula. Okay, that's the procedure here. I'm going to show you why it works, and I'm also going to show you how to choose u and dv wisely. But this is the basic procedure, so we have to be comfy with this. And there is an element of choice, like Hutanji was saying there. In that step where you choose u and dv, you could choose them a bunch of different ways. So there's no fixed way to do it, at least not from the theorem, not from the formula, but I will give you some guidelines. Okay, so we're going to talk about how to choose u and dv in step 1. The rule here is called LIPET. L stands for logarithm, or log. I stands for inverse. P stands for polynomial. E stands for exponential. T stands for trig. What this is a hierarchy. If there are any logarithms in your integrand, then you should choose that to be u and let dv be everything else. So here's, let me choose u according to this LIPET rule, then let dv be everything else. So if there are any logs in my integral, I'll pick u to be the logarithm function and let dv be everything else. If there are not any logs, then I look for any inverse functions. If there are any inverse functions like arctan or the inverse sine function, then I'll choose u to be that and let dv be everything else. So this is a hierarchy. I'm going to misspell this word, I'm sorry. For choosing u. If there are any logs, let, oh damn, it's a brand new pen. Let u be those, be that, and dv be everything else. If there aren't any logs, god damn it, about to give up on this pen. Look for inverse functions. And so on. So when you're handed your integral and you've decided to do integration by parts, what you need to do is pick a partition. Choose something to be u and everything else to be dv. This rule tells you how to pick u. If there are any logs, you'll let u be the logarithm function, and everything else will be dv. If there are not any logs, then you look for inverse functions. Are there any inverse functions? If yes, you'll let u be the inverse function, and everything else be dv. If there are neither any logs nor any inverse functions, then you'll look for polynomials. Are there any polynomial functions? If yes, you'll let u be the polynomial function, and everything else will be dv. If there are not any logs, inverse functions, or polynomials, then you'll look for exponential functions. If there are any exponential functions, you'll let u be the exponential and dv be everything else. That's the idea, right? So this is a hierarchy for choosing u. Once you've chosen u, you'll let dv be everything else in the integrand. Yeah, sure. So this is a little bit complicated. Remember what we're trying to do? We're trying to pick a way to partition our integrand. I'm trying to pick a way to split my integrand into u and dv. This is a hierarchy for choosing which piece to call u. If your integral has a log in it, you'll pick that piece to be u and everything else to be dv. If your integral doesn't have a log in it, then you'll start looking for inverse functions. Does my integral have an inverse function in it? If yes, then you'll pick that to be u and everything else to be dv. If my integral doesn't have any logs and doesn't have any inverse functions, then I'll start looking for polynomials. Does my integral have any polynomials in it? If yes, then I'll let that be u and I'll let everything else be dv. If I don't have any logs or inverse functions or polynomials, then I'll start looking for exponential functions. Does my integral have any exponential functions in it? If yes, I'll pick that to be u and everything else to be dv. Okay, so this is our IBP procedure. You're lucky. Nobody gave me this shit when I had to learn it. They just showed me the formula and were like, pick u and dv however you want. Some ways will work, some ways won't. And then later when I was in grad school teaching it, an undergrad actually showed me this. And I was like, oh shit, that's so useful. I'm going to show that to my students when I teach this in the future. So here we go, right? This is the cheat code for integration by parts. But really, IBP is just the formula. You can pick u and dv however you want. If you pick u and dv according to this rule, right, you use this rule to pick u and you let dv be everything else, that will solve 99% of IBP problems. So let's run through this procedure for a few more. Okay. So we take a look at this guy. I go, oh shit, I have no idea how to integrate this. It's definitely not a substitution problem. It's definitely not an obvious antiderivative. So I had better use some integration by parts. I see my integrand is the square root of x times the natural log of x dx. I have to split this up. One piece here I have to call u, and everything else must be dv. So I think about my Lipet rule. Are there any logarithms here? Yes, there are. There's this guy. So I know I'm going to run IBP. And that means I have to pick u and dv to get started. According to my Lipet rule, I should choose the logarithm piece to be u and everything else to be dv. This looks like that. So I've chosen u to be the log and everything else is dv. Okay. Then I calculate du from u. Du is 1 over x dx. I calculate v from dv. That's 2/3 times x to the 3/2. Why? Because this is x to the 1/2. If I integrate that, I add 1 to the power, divide by the new power. Adding 1 to the power 1/2 gives me 3/2, so that's my new power. And then dividing by 3/2 is the same as multiplying by 2/3. So these power rule integrals, we should be very fast at by now. Any questions on how I filled out my IBP table? On how I calculated, how I chose u and dv, and how I calculated du and v? Okay, so now my step 2 is just plug everything into the IBP formula. The integral of u times dv. I divided by 3/2, James. So this would be x to the 3/2 divided by 3/2. Dividing by 3/2 is the same as multiplying by 2/3. So go off to the side and do the integral of square root x dx. Right, I integrated this to get this, that's all. Do we see it? All right, don't want to get too sidetracked. Like this. And if I was doing this as an indefinite integral, I would write a plus c here. But because I'm doing it inside my IBP table, I don't worry about the plus c. Okay. All right, so then I come down here and I plug all of this into my IBP formula, which says the integral of u times dv should be u times v. So that's ln x times 2/3 x to the 3/2 minus the integral of v times du. Like so. And now I simplify everything in here and I ask, has life gotten better? Are things improving? I can also clean this up a little bit. That's 2/3 ln x times x to the 3/2 minus, I can pop the 2/3 out of this integral, and then x to the 3/2 divided by x, or x to the 3/2 times 1/x, that's x to the 1/2. So I'm just doing algebra in this step, no calculus, just algebra. The power here is still a 3/2 power. Everybody sees how this simplifies to this. I'm using that rule that x to the a divided by x to the b is x to the a minus b. So 3/2 minus 1, that's 1/2. And now finally I can do that integral. It's not a hard integral. Here, if I integrate x to the 1/2, that's the same integral I did earlier. That's going to be 2/3. So I'll get another 2/3 x to the 3/2. And now, because there are no more integrals, I slap on my plus c. And we can clean it up a little bit. Like this. Okay, so always really what I'm using is that formula, u times v minus the integral of v times du. U times v minus the integral of v times du. And then you write this line down and you ask, have things gotten better? If things have gotten better, you proceed. Here, I say things have gotten better because I don't have any logs in my integral anymore. And logs are kind of hard to handle. So once they're gone, I'm happy. This is now just a power function, right? Power functions are easy to integrate. So I've gone from a power function times a logarithm in my integral to just a power function in my integral. That's definitely a step in the right direction. How are we on time? I'm torn between showing you more examples. Yeah, we got time for one more example before I try to show you why this formula works. Last call for questions on this guy. Everybody can see the formula here. This is goddamn pen, u times v minus the integral of v du. Okay, let's do one more example here. And then I'm going to do my best to show you why the formula works, show you how it really is just a backwards product rule. But before we do that, one more little bit of practice. Here I'd like to integrate x squared times e to the x. So again, I recognize that there's no substitution that'll make this integral easy. There's no obvious antiderivative. It's not one of our Calc 1 things, and it's not a substitution thing, so it's got to be something new. The new thing is integration by parts, so I should try integrating by parts, which means I need to split this up into u and dv. So I think about my Lipet rule. Do I have any logarithms? No, I do not. Do I have any inverse functions? No. No arctan, no inverse sine, no none of that. Okay, so then do I have any polynomial functions? Yeah, here, look, x squared, that's a polynomial. So I'm gonna run IBP with u equal to my polynomial piece and dv equal to everything else. So that u times dv is my whole integrand. So then du, that's going to be 2x dx, and v is going to be e to the x. And if I run my formula now, the integral of u times dv should be equal to u times v minus the integral of v times du. That's x squared times e to the x minus the integral of 2x e to the x dx, right? This times this minus the integral of this times this. I ask, have things gotten better from the original to here? Well, I've got this piece up front. I don't really care about that. He's not inside an integral anymore. He's done. But I still have this integral. And this is still a hard integral. But this is a polynomial times e to the x. It's the same sort of thing we started with. And if I did this just one more time where I pick this piece to be u and this piece to be dv, then this piece will differentiate to a constant. So what I need to do here is run integration by parts one more time. Now, normally what I would do here is I would pop out the 2. And look fresh at this guy. This is actually a problem we solved earlier. Remember? This was the very first example we did, the integral of x times e to the x. And that was an IBP thing on its own. So in other words, what we do here is we run integration by parts twice. So here I'll let u be x and dv be e to the x dx. du is then dx, and v is e to the x. And I'm running IBP just on this piece, so everything else is going to stay the same. I'll still have my x squared e to the x here, and then I'll have minus 2 times, and I'll open up a big parentheses, because I'm about to replace this guy by his IBP equivalent under this table. So the integral of x e to the x dx should be x times e to the x minus the integral of e to the x dx. And all that goes in these parens. So here's the first use of IBP. Here's the second use of IBP. And then we distribute the two. And the integral of e to the x dx is just e to the x. So you get x squared e to the x minus 2x e to the x. Oh, and when I distribute this minus, this is going to become a plus, isn't it? I'm distributing a minus 2, so the minus goes here and here. So this will be actually a plus 2 e to the x, and then at this stage I start writing my plus c. So what I'm doing is I'm distributing the minus 2 to both of these guys. This is a common thing. You run IBP twice. Sometimes you'll run IBP 3 or 4 times. If you wanted to integrate x to the n times e to the x, that would require n applications of integration by parts. Each time you would choose u to be the polynomial piece and dv to be everything else. You might notice a pattern here. And I encourage you to look for patterns. There's another way to write this stuff down called tabular integration by parts, which is not an official part of the curriculum here at Santa Fe. It is an official part of the curriculum at UF. So if you intend on transferring to UF, where they will assume that you took Calc 2 there, or you are at least comfortable with Calc 2 as it's taught at UF, you may want to read about tabular IBP. And again, if you look in the modules that I've posted to Canvas, there's a resource there for tabular integration by parts. But first, make sure you're comfy with the basics. It is pretty awesome. I agree with that. The pattern you may notice here is, x squared, 2x, 2. That's a sequence of derivatives. And e to the x, e to the x, e to the x, that's a sequence of antiderivatives. So they've been slapped together. And then the signs alternate, and that is the pattern. But questions on just the pure execution here, how we made this go, why we wrote down what we wrote down. There is no benefit to U sub over IBP. It's just that they work on different things, like the chain rule works to differentiate some things and the product rule works to differentiate some things. Think of U sub as your backwards chain rule and IBP as your backwards product rule. They work on different stuff. Sometimes you'll combine them. Sometimes you'll do a little U sub, then you'll do some IBP on the resulting integral, which is why you should never actually use the letter U in your U sub, because you don't want to do something like, say, U equals U squared. That would be bad. That would be overloading the variable U. But yeah, no preference between one or the other. They're both great techniques and you'll use both. Now, one more example problem. It's hard to stop doing examples. Examples, I think, are the most important way to get this stuff into your head. So one more example problem, and then I'll show you the proof, because the proof, I think some people find it very enlightening, but most people do not. Okay. Those who know me know how much I love the inverse tangent function. Tragic that until now we haven't been able to integrate the inverse tangent function, but I claim that now we can. It's not going to fall to a U sub. Doesn't look like any of the U sub problems we've seen. Not going to fall to any of our other techniques, right? I know the derivative of arctan, but I don't know the antiderivative of arctan. So it's got to be an IBP thing. We call that lecture logic. So here, according to my Lipet rule, do I have any logs? No. Do I have any inverse functions? Yeah, this is an inverse function. Inverse functions are functions defined as the inverses to other functions. So arctan is defined to be the inverse of the tangent function. So I'll pick that for you. And everything else to be dv. Well, what's everything else? It's just dx. This means that du has to be 1 over 1 plus x squared dx, because that's the derivative of the arctan function. And v, we integrate on both sides, v has to just be x, because the integral of dx is just x. So then according to my IBP formula, and now I'm using the formula for definite integrals because this is a definite integral, I'll have u times v evaluated between bounds. So that's the inverse tangent of x times x itself evaluated from 0 to 1 minus the integral from 0 to 1 of v times du. And my recommendation for these is to always go ahead and knock out that evaluation piece. Don't wait. So otherwise you might forget to evaluate. If I plug in 1 here, I get inverse tangent of 1 times 1. The inverse tangent of 1 is pi over 4. So I have pi over 4 times 1 minus the inverse tangent of 0 is 0, and 0 times 0 is 0. So that's our evaluation. And then over here, I can do some algebra to rewrite this piece as x over 1 plus x squared dx, if we wanted to. So of course, 0 times 0 is 0. That first piece, everything there is just pi over 4. Well, really is gross. Just let that sit and try and for a minute or something. The integral that's left over here is not entirely trivial. We're gonna have to think for a second about how to do that. This is actually a little u sub problem. So my first piece here is pi over 4. That's all well and good. The integral that's left over though requires u sub. So here I'm gonna I won't use the letter u because it's confusing. I'll let z be 1 plus x squared. Sub for the bottom. Then dz is 2x dx. Also, I'm doing this in a definite integral, so I need to change my bounds. When x is equal to 0, z is equal to 1 plus 0 squared, that's 1. And when x is equal to 1, z is equal to 1 plus 1 squared, that's 2. So there's my substitution. This first piece is just pi over 4. This integral under that substitution will be minus. I've got 2x dx here, and I've got x dx here. So 1/2 dz is equal to x dx. So I'll have a 1/2 pop out. My integral, which used to run from 0 to 1, now runs from 1 to 2. And what's left? The x dx has been soaked up by dz. So this will just be 1 over z times dz. You see the 1 plus x squared downstairs, that's the z. The x dx upstairs is 1/2 dz. So that's the dz here and the 1/2 I pop out. So altogether, we get pi over 4 minus 1/2 times the integral of 1 over z dz is the natural log of the absolute value of z, and that has to get evaluated between his new bounds 1 and 2. So this is pi over 4 minus 1/2 times the natural log of 2 minus the natural log of 1, and the natural log of 1 is 0. So this is pi over 4 minus 1/2 times the natural log of 2. And that's the integral of arctan from 0 to 1. The indefinite integral of arctan and many others will be for you to do in your homework. But it's crucial that you're comfy with this IBP process. So any questions about the integration by parts step here, this first step that came from this box? The rest of this problem is a 5.5 problem. It's a U subproblem. Okay, so then I'd like to take the rest of the class time to try and convince you why this shit is true, because it's a little bit weird. It's not super obvious. On Wednesday, I'm going to be showing you some harder integration by parts problems. Just as a heads up, this is not the end of IBP, this is the beginning. IBP can get considerably more complicated. We'll be applying it to some trig functions and some more complicated functions. If you've ever heard of a damped harmonic oscillator, we'll be looking at that classic problem from physics. But before we do that, I would like to convince you that IBP works. And the easiest way I could do that, I think, is probably by showing you some stuff that I've already posted. So if you come here, of course, you got the review material. This is good stuff. You got the stuff we've been working on. If you haven't checked out these visualization videos that I added for cylindrical shells and the disk washer method, please do that. But then come down here. So some proofs. We'll start here. So these last two examples, especially this last example, this is the sort of stuff we'll be looking at on Wednesdays, how things can get a little bit harder. We did a problem like this where you use IBP twice, the x squared times e to the x piece. But come through and look at these Patrick JMT videos. They'll help you get a handle on what we're doing, and they'll show you more examples. I don't know why that's trying to do that. They changed canvas. But here's one way of thinking about this. Let me first come back here for a second. If you take the IBP formula, which is the integral of u dv equals uv minus the integral of v du, and you rearrange it, that says that uv is equal to integral of u dv plus the integral of v du. Right? Let's imagine, first, let's make sure we're comfy with this. This looks familiar now. This looks like a product rule. If I come through and differentiate, and I'm going to do this very sloppily with the prime notation, this says that u times v primed is equal to, well, what does the prime and the integral do? They just eat each other up. So this is u times dv plus v times du. This should look very familiar, right? This is just one way of writing the product rule. the derivative of u times v is equal to u times the derivative of v plus v times the derivative of u. Okay, so the IBP formula is equivalent to the product rule. Step one in convincing you that this shit works. You know the product rule works, and this is just a rephrasing of the product rule in terms of integrals. Okay. To me, this is the most convincing thing. Simple, it's algebra, but this step might feel weird to some people. What are we doing going from here to here? We're just saying that the prime and the integrals undo each other, because if you differentiate an integral, we know that those are opposite operations, right? Antiderivative, derivative. There is another way of thinking about this. The picture proof. If I call this my u-axis, and I call this my v-axis, and I think of this as a function, graph of some function, then if I read it like this, then I'm saying v is a function of u. And if I turn my head, then I'm saying u is a function of v. Right? So normally like x and y is a function of x is a function of y. I can ask myself, what's all the area encased in this box? On the one hand, if this point is u comma v, then all that area is the width times the height, which is u times v. On the other hand, if I think of this area down here as coming from the integral of this curve taken with respect to this variable, then this guy is the integral of v du. And this guy over here I could think of as the integral of u dv. So u times v, the total area, would be equal to the sum of those two integrals. And again, you get your integration by parts formula. You just have to rearrange. You subtract this piece over. And the Stack Exchange post here has a much more convincing version of this picture, where they actually make it work for all the specifics, the bounds and stuff. But I encourage you to think of this, right? Think of it like this. Think of it the first way I showed you. This is the easiest way to really understand how integration by parts is related to the product rule. But this picture proof I found to be useful also, right? If my horizontal axis is here, the v-axis, no, it's like I've done it, here the u-axis and here the v-axis, then the two gray areas you can interpret as integrals. And then also you can interpret the collective area as the product. So you've got u times v equals integral v du plus integral u dv. That's what we wanted. Okay. So this is about all we have time for today, right? I think the simplest way to trust IBP is to think of it like this. But whether you trust it or not, what matters in this class is that you get good with it. So you got to put in the time. The LIPET rule will save you in 99% of integration by parts problems. The LIPET rule will do the job. So use LIPET to pick u, let dv be everything else. Then just run your formula. When you do that, make sure you're paying attention to whether you're working with a definite integral like this or an indefinite integral like the other ones we looked at. If you're working with a definite integral, make sure you don't forget to evaluate this first piece, the u times v piece, between bounds. Don't forget to write this part here, and don't forget to evaluate it right away. Don't wait till the end to do the evaluation for this piece. Evaluate this piece right away. It'll save you time. And then remember that the integral you write down at the end is also between bounds. So the two different forms of that, or versions of that formula, one for definite integrals and one for indefinite integrals, make sure you have these straight. If you're doing integration by parts on an indefinite integral, it's easy, you know. If you're doing it on a definite integral, make sure you remember that every single piece gets the bounds. People tend to forget this piece getting bounds. Sometimes people forget that the integral at the end has bounds. Just remember, if the integral you started with has bounds, every piece that you get as an output from the IBP formula will also have bounds. Okay. All right. So this is where we're going to leave it for today. If you need more time on the homework from last week, you can submit an extension request in WebAssign. I went through them a few times over the long weekend, clearing them out. So if you submitted an extension request yesterday or the day before, it should be taken care of, unless you did it towards the end of the day. I'll be going through and checking those in a few minutes here. But also, of course, there will be a new homework opening up this week. And the new homework is going to be on integration by parts. So I encourage you to spend some time on the homework today, wherever you are in it. If you are still on last week's stuff, please try to get that totally wrapped up today. If you are done with last week's stuff and ready to move forwards, then watch for the new homework to drop. It'll be opening up. I have one more class after this, and then I'll open up your new homework. It'll have a bunch of IBP stuff in it. Sometimes you'll have to do a substitution first. Some of the IBP problems will be things that we haven't talked about yet. So if you see like a sine times e to the x, or cos theta times e to the 2 theta. We don't know how to handle those. The only other things that we don't really know how to handle from today's lecture are what are called looping integrals, like odd powers of secant times even powers of tangent. And we will attack those as well on, I said Wednesday before, on Friday, right? Because today is Wednesday. We're behind this week, the holiday. So that's where we're at. Watch for the new homework, finish up the old homework. If the old homework ain't done and you haven't requested an extension, go ahead and request an extension. I will grant it in just a few minutes. And then we're gonna move on from here, okay? All right, any questions before I end the meeting? Okay, then I hope you guys have a lovely rest of your morning. I will see you on Friday. And again, just remember to be working on the homework.